We will get started. I know that I haven't seen any of you before, so I'll just do a quick introduction. I'm Captain Christopher Woods, and actually I've got a little bit more of an introduction on the next slide. Today we're going to be doing 4 periods of meteorology today, and as usual 4 periods of 40 minutes. And we will get started since there is quite a bit to cover. Like I said, I'm Captain Christopher Woods. I did both the GPTC and PPTC some time ago. And then I've been a glider instructor for quite a while. So I was instructed in Atlantic Region 2014, and then 2015 to 2023 in Eastern Region, as well as a little bit in 2024, but not quite as much. Other than that, I'm also an officer at 1 Squadron in Montreal. I'm a gliding instructor at the Saint-Jean Cadet Flying Site. And in my civilian life, I'm a flight simulator test specialist on full flight simulators. So with that out of the way, let's get started. Okay, and I've got the chat there, so I should be able to see that. I'm hoping, actually just to double check, can someone just, I think I should be able to, actually never mind, I should be able to see if everyone raises their hands. Worst case, just put a message in the chat if I seem to not miss it, or seem to miss something for quite a while. It's been a while since I've used this Teams functionality. All right, so what we're going to cover in the first period, so we're going to go through the different classifications of clouds, different types and of clouds and how to recognize them, and then fog, how it's formed and the different types of fog, and then lastly, obstructions to visibility. All right, so the classification of clouds. So basically, the clouds are classified in 2 main ways. First off is by their height, and second is by their shape. So we have the 4 families of clouds, which are basically categorized by height. So we have high, middle, low, and clouds of vertical development. And then we have the 2 types of clouds, which are categorized by their shape. So we have stratiform, also called stratus clouds, and we have cumuliform, also called cumulus clouds. And we'll go through all of these in more detail in the coming slides. So for the high clouds, which are often, which are the names of these the clouds in this category will often have 0 in the name to help us identify where those clouds are. So these are clouds which are very high up in the atmosphere. So they're cloud bases, so the bottom of the cloud is between 16,500 feet and 45,000 feet. So these are the highest clouds that we have in the atmosphere. And because they're so high up and it is very cold in the higher layers of the atmosphere, these clouds are consequently composed out of ice crystals. So the different types of high clouds. So first of all, we have cirrus clouds. And a lot of these cloud descriptions are going to be very artistic descriptions of what the clouds look like. Sometimes they look like what the description says. Sometimes you have to use a little bit of your imagination, but we'll do our best. So the cirrus clouds is these very thin wisps of clouds. So very high up in the atmosphere, you just see these little thin wispy bits. The description they say is like it's made with an artist's brush or cat whiskers or mane's tail. I'm not sure I see many of these, but some people might. And because these clouds are so high up, they will generally have no significance to flying. They don't really have any significant weather, and they're usually well above any of the aircraft that are flying there. And they will generally indicate a stable layer of air. Do we know what stable air means? I don't recall if that was been covered in a previous week. Yes, can anyone remind us what that stable air would mean? Just type it in the chat, or if not, I can just remind us. Give you a sec. All right, so stable air is when the air doesn't want to significantly climb or descend. So if it's displaced, it's going to return back to where it was. So if it's air that generally isn't rising. Okay, next. We've got our cirrocumulus clouds. So these are, again, descriptions are thin cotton-like clouds. This picture doesn't really capture the next description, but sometimes you can see it a little bit better where it looks like the pattern of sand at the beach, where it's like these little waves. This picture is not super clear, but sometimes you can see it a little bit better than that. Oh, sorry, I missed. We did get an answer from Cadet Cook about the stable air mass. Oh, there we are. Yeah. Cool. And yeah, the cirrocumulus clouds generally is not really a clear indication of any future weather conditions. Again, very high up and not really too much of a concern for us when we're flying. And then lastly, for our high clouds, we have the cirrostratus type clouds. So these are a thin, high sheet of clouds. They're kind of translucent, where in this picture here, we see the sun, and the sun is still visible through the clouds, and it can produce this halo effect. And these will often indicate the approach of a warm front or occlusion. So they can be a sign that the weather over the next period of time is going to get worse. And we'll talk about that in a little bit more detail later on this evening. Right, so that is it for the high clouds. Moving on to the middle clouds. So these clouds, are clouds where the cloud base is between 6,500 feet and 23,000 feet. And these can be a mix of ice crystals and water droplets because they're a little bit, in this area, it's a little bit warmer than the high clouds, but it can still be quite cold. And usually there isn't very much turbulence unless there's cumulus clouds, which we'll talk about in a little bit. So 3 types again. So first off, we have the altocumulus. So you probably may have noticed so far that some of these names have cumulus, some of these names have stratus or strato. If you remember, there's the categories and there's the types of clouds. So they're the altocumulus cloud, the cumulus clouds have certain characteristics. The stratus clouds have certain characteristics, and it'll all start to come together in a little bit. So altocumulus clouds are these little lumps of clouds that are high up in the atmosphere, and again, sometimes they're associated with a front, but a lot of the time they have no value for predicting future weather. So they're just these little clumps of clouds that are very high up. So next we have altocumulus castellanus. So the castellanus bit is this, indicates that they have these turreted edges where there's these bits sticking out. And these may develop into something called cumulonimbus, which we'll talk about later, but essentially is a thunderstorm. And so this is a variation of the altocumulus, which is a little bit more vertically developed. So it started to grow upwards a little bit. And these will have the characteristics of unstable air. So you'll have some turbulence, you'll have some showery conditions, and unstable air. And then lastly, for this category, we have the altostratus type clouds. So these are, it's a stratus type cloud in the middle category. So this is generally a thick layer of gray cloud. Sometimes it can be slightly translucent, but a lot of the time it will be an opaque gray layer that you can't see through it. Often it's going to indicate the approach of a warm front that's coming fairly soon. And we might get some light rain or snow. There may be some icing, and they will be associated with stable conditions. All right, so next category is the low cloud. So these are clouds where the cloud base is between the surface, meaning the ground, and 6,500 feet. So this is the area where for gliders, for general aviation on the power course, most of the time we are a little more likely to be flying. And these types of clouds can be composed of water droplets, supercooled water droplets, and ice crystals. And a supercooled water droplet is a water droplet that is below the freezing point, so it's below 0 degrees Celsius, but has not actually frozen solid yet, which can happen in certain conditions. All right, so the first type of cloud in the low clouds category is stratus clouds. So this, to be honest, this picture doesn't really quite capture what it looks like exactly, but usually this is a thick, low layer of cloud. So when you go outside and it's just all gray everywhere all day, and there's maybe a little bit of rain, that's in little, not heavy rain, but just like light drizzle, it's probably a stratus cloud. So it looks like fog, it's not, but it's not touching the ground. And a lot of the time there will be low visibility, drizzle, and fog. And again, it's a sign of stable conditions. Next we have stratocumulus clouds, which are, it's either a layer or little masses of cumulus type clouds. Unlike most cumulus clouds, it's a sign of stable conditions. Sometimes there is some light precipitation. And they say here it's common in high pressure areas in the winter. That's a very specific point to keep in mind. Yeah, so there's that. And then lastly for this category is nimbostrata. So anytime a type of cloud has either nimbo or nimbus in it, that means it's associated with precipitation. So rain, hail, snow, anything like that. So nimbostratus means stratus clouds with precipitation. And this is going to be a very dark gray, thick layer of low cloud associated with rain. So it's like altostratus, but it's gotten substantially thicker, often associated with warm fronts, which we'll talk about later, and will have continuous, steady rain or snow. They can be quite thick. They say here up more than 15,000 feet thick. VFR operations often are going to be difficult because these clouds are low, very thick, and accompanied by rain. So it could be not ideal conditions to fly in. And a sign of stable conditions. More or less all of the stratus type clouds will be a sign of stable conditions. Questions so far? Okay. And the last category, the cloud that we're going to cover for now, are the clouds of vertical development. So vertical development generally means clouds that are growing upwards as a cause, which are caused by rising air. So these can form as low as the ground, can be formed of water droplets, ice crystals, or supercooled droplets. They may be an isolated cloud, so they're just one cloud on its own moving around, or it could be embedded inside of a layer of cloud. So it could be a layer of some sort of stratus type cloud with an embedded cloud of vertical development. And because these clouds need rising air to be developing vertically, they're a sign of unstable conditions, because those are the kind of conditions you need for rising air in a substantial amount. So we've got a bunch of different types of clouds. So we have cumulus. So these are, I think we'll go through these. Yeah, we'll go through them one at a time. So we have the cumulus, towering cumulus, cumulonimbus, and altocumulus castellanus. So cumulus are the clouds that you think of when you think about just looking outside and looking at clouds and trying to find shapes and stuff in the cloud. So the ones that are these irregular shapes that are fluffy, like the picture you can see here. So they say, they say resemble cotton balls, but they're the weird irregular shaped clouds that can make all sorts of different shapes. They will generally have a flat base at the bottom, and then above that they'll make all sorts of shapes, but the bottom is usually relatively flat. They will form, let's see, is anyone else having a screen difficulties? If the screen is working, can I see some thumbs up if the screen is working? Is that a yes, it's working, or a yes, it's not working? Sorry. Okay, give me 1 second. I will try to resolve this. Thanks for letting me know that we're having difficulties. Wow. All right, I've restarted the sharing. Let me know if it's working. Nope. Is this a widespread problem, or is it just for a handful of you? Interesting. I did the same thing as I'd done the first time, so that's okay. All right, we'll try again. We'll try sharing a full screen this time. Maybe this will be better. Right. Okay. Well, keep trying different options here. Give me, let's see. Still no change? All right, give me 1 minute. I will change browser and try something else. Sorry about that. Give me 1 minute. Yes, thanks. All right, so it seems like we are back. We'll continue on from here. Unless, how long did it stop working for it before everyone let me know? Did we miss something? If I need to go back, I will. If not, I will. All right, I will carry on. Excellent. There we go. So we're talking about the cumulus clouds. So, like we said, these are those general fluffy clouds you can think of. The bottoms are generally flat bases. Above that, they're regular shapes. How high the clouds are depends on the difference between the temperature and the dew point. Have we learned what the dew point is before? If not, we can talk about that shortly. Okay, so uh, the dew point is going to be the temperature that the air needs to be cooled to for it to become saturated and for water vapor to condense into liquid water. So that's generally going to be the temperature where clouds or fog starts to form. So the difference between the temperature on the ground and the dew point is generally going to indicate roughly how high the clouds are. Cumulus clouds generally will have light or moderate turbulence, but no precipitation, which is fairly important. And it's a sign of unstable conditions, like all of these clouds of vertical development. Next, we have the towering cumulus cloud. So this is a cumulus cloud that has continued to develop vertically. So it started growing upwards, and it's going to make this big tower of cumulus. On a bright, sunny summer day, you can often see these clouds growing fairly quickly, which can be kind of cool to see. But it's a sign that the conditions are interesting for flying. So there can be some fairly serious turbulence. Inside the cloud, there can be some icing. There's often rain showers or snow showers, and the air underneath these can be fairly rough. Again, a sign of unstable conditions. And when these towering cumulus clouds are appearing and growing quickly, it's a sign of a day where we have to be very careful for the potential of thunderstorms to just pop up fairly quickly. Which leads us into the cumulonimbus or CB type of cloud. So we said before that nimbus or nimbo means precipitation. So this is a cumulus cloud with precipitation, but this is essentially a thunderstorm. So the towering cumulus continues to develop. We get this cumulonimbus type cloud. So often we can see this anvil type shape, although this is usually more as the storm is dissipating. You'll get gusty winds, you'll get rain or hail, heavy icing, turbulence, showers. Should be avoided in a sign of very unstable conditions. Again, this is a thunderstorm. Flying through this would be undesirable. So that's it for the different types of clouds. Any questions for that so far? If not, we'll move on to the next thing. Important note for clouds. I don't know if we really discussed this, but so clouds they form when water vapor condenses into liquid water. So and the two main ways that will happen is either by cooling the air down until the air reaches the dew point, which point it condenses, or by adding more water into the air. And that'll be important to understand how fog forms, because that forms in essentially the same way. So fog is a cloud that is in contact with the ground. So very similar to clouds, or it is a cloud, but it's just a little bit more of a specific subtype. And as the temperature approaches the dew point, the water vapor condenses and forms clouds. So this is essentially what I just said. So there's a bunch of different types of fog. We will cover all of these in the next subsequent slides. So the ones that are formed by cooling are radiation fog, advection, and upslope. And the types of fog which are formed by adding moisture are the steam fog, ice, and precipitation induced. So first of all, we have radiation fog. So this fog will typically form at night as the Earth. So during the day, the Earth is warmed by the sun. At night, the Earth isn't, there's no sun out anymore on this part of the Earth, so the Earth will cool down. And by radiation, the air that's just above the Earth will also cool down. So it forms at night. Sometimes it thickens or forms at sunrise, but usually it's at night. As the sun starts to heat the Earth, it starts to form a little bit of turbulence. Yeah, so these are the things that I just mentioned. So as the air cools down, or as the Earth cools down, it cools down the air above it. If the air is cooled down to the dew point, you will start to get fog. So the conditions that will favor this are it's clear, so a clear night, so there's no clouds, the air is moist, and there is relatively light wind. So you get this fog that forms overnight and typically breaks up throughout the morning as the sun rises. Next, we have advection fog. So this is what happens when we have warm, moist air moves to a colder area and then gets cooled down by advection. So this can happen when there's a bit of a stronger wind, which is moving the air around a little bit more. Often happens in areas near large bodies of water because typically the water is colder than the land. It can last for quite a while. So we have our air moves from the warm land to the cold water, and we'll get some fog. And then next, for the last one that's in the cooling category of fog, we have the upslope fog. So as warm, moist air is pushed up a slope, so up a hill or a mountain, as it rises, air will expand, and as air expands it will start to cool down at the same time. So we have a wind blowing the air up the hill. As it rises, the air expands. Because it's expanding, the air will cool down. And if it reaches the dew point, then we're going to get some fog. Next, we have steam fog. So these next three types of fogs are fog which occurs when moisture is being added to the air as opposed to the air being cooled down. So when we have cold air moves over a warm area of water, there's going to be steam coming off of the water. So there's going to be a little bit of evaporation into the cold air. And as water is added to the cold air, it will gradually start to become saturated. Once the air is saturated, we will start to get fog. And it occurs over rivers and lakes, so over bodies of water, typically when the weather is a little bit cold. So say in the fall. Next, we have the precipitation-induced fog or frontal fog. So this is what happens usually with a warm front that we're going to talk about later on today. So we have a warm front, which we'll talk about later, but essentially we have some clouds with some light precipitation and stable air. After the rain lands, it's going to start to gradually evaporate into the air, and adding all that moisture into the air can eventually cause it to become saturated and cause fog. And then lastly, we have our ice fog. So this happens when it's very cold out like it most likely is right now. When the air is moist and the air is very cold. When the air is very cold, the dew point is going to, or the amount of moisture that the air can hold is quite low. So not a lot of moisture can actually be added into the air. So anytime any water vapor is added into the air, it will pretty much immediately cause fog, create visible ice crystals. You can think about, when you see your breath when you're outside on a cold day, it's the same principle. Is you're adding this warm, moist air into the atmosphere that's very cold, and that's going to cause a little bit of mini fog. And you can see that when an engine started or coming out of your car's muffler or anything like that. So there's water vapor, and then there's nuclei, condensation nuclei that are coming out in the exhaust, and that can cause a little bit of localized fog. All right, last teaching point for this lesson is our obstructions to vision. So there's two main ones we're going to talk about today. So we've got haze and smoke. So haze is a mix of different particles of water droplets, dust, salt particles, all sorts of other little things in the air that you can't see them individually, but it can start to restrict visibility a little bit. So often, we look at the smog around a city, this little bit of obstruction, and it really becomes an issue when the air is very stable. So if the air is stable, it's not moving around a lot. There's nothing to really mix up the haze and move it away, so it can sort of settle and start to obstruct your visibility. So stable conditions, that's why stable conditions will often have worse visibility than unstable conditions. And then lastly, we have smoke. So if there's smoke in the air, in the atmosphere, that can cause some obstruction to our visibility as well. So smoke from a fire, from something like that. A few years, depending, and often in the summer, if there's forest fires in one area, there can be smoke obstructions, hundreds of kilometers away that can cause difficulties for flying. So it can be a bit of an obstruction. Then there's a little reminder here that from air law, we can't go flying over forest fires, just to keep that in mind, or within 5 nautical miles, but would not be a good idea anyways. Any questions? All right, so this one, very quick reminder of what we just saw. So the two different types of obstructions to vision that we can see in the atmosphere. Anyone? Yeah, haze and smoke. Very good. Yep, thanks. And last one. Okay, this one is a little bit, so what are the 6 different types of fog and how are they formed? So I'd like, let's say if different people can list one of the types of fog and how that type of fog is formed in a very short description. Just or even if we can just name them, we can maybe make this work. Okay, we got radiation fog, good. 1 down, 5 to go. Ice fog, good, with a description, even better. All right, advection, good. We got half. Okay. Upslope, we got the description, good. All right, we're missing advection. We're missing 2 more. Frontal fog or precipitation induced, yep, and steam, there we go. All right, so radiation fog is caused as the Earth cools down at night. Convection is when the warm, moist air moves over a cold area, often a body of water. Upslope is as moist air is being blown up a hill, expands. Steam is when we have cold air moving over a warm body of water and we get evaporation. Precipitation induced is associated with a warm front as the rain evaporates, and ice fog is moist air when it's very cold out. All right, good. So we will move on to the next section with winds and air masses. So we've got a lot of points to cover, and we will get right into it. So we're going to cover pressure gradient, factors affecting wind direction, squalls and gusts, diurnal effects, land and sea breeze, katabatic and adiabatic winds, air masses, how the air masses form and how they're classified, how they're modified, and seasonal effects in North America. So we will get right into it. So before we get into too much detail, what is air or atmospheric pressure? If anyone can, does anyone have a short description for what pressure is before we get too much into the weeds on maps and stuff? Yeah, so atmospheric pressure is caused by the weight of the air above us, but really, fundamentally, it's how much the air is pressing on all the surfaces around it. So, but good, that's the cause of it. And so we can measure the pressure at various points on a map and create a weather map like this, where we can see the pressure at different points. So the pressure gradient is the rate of change of pressure over a given distance. So in a certain amount of horizontal distance on our map, how fast is the pressure changing? These lines here on our map are called isobars, and these will join areas of equal pressure. So for example, this line over here, everywhere along this line, the pressure is 1,004 hectopascals. So it's showing areas of equal pressure. The closer these lines are together, the steeper or the bigger the pressure gradient is, and that's going to be often associated with strong winds. So if any of you have done map and compass, sorry about that. If any of you have done map and compass and seen topographical maps, it's very similar to the contour lines on those types of maps, where steep, very close contour lines indicate that there's a steep hill. Here it's a very steep pressure gradient. So in this area here, where the isobars are very close together, it's going to be a steeper pressure gradient than this area over here, where the isobars are very far apart. Typically, they are 4 hectopascals apart. So we'll move on to how that affects winds in a little bit more detail over here. So generally, air wants to go from a high pressure area to a low pressure area. So if you have high pressure in one place and low pressure somewhere else, the air wants to go from the high to the low. So if you have you inflate a balloon, you fill it full with relatively high pressure air, that air wants to go out of the balloon. So if you open it or let the air out, it's just going to go out to the low pressure. However, the Earth is spinning, so that makes things just a little bit more complicated than that. So the air can't go directly from the high pressure to the low pressure. Because the Earth is spinning, there's something called the Coriolis force, which is going to cause the air to be, instead of going straight from the high to the low, it's going to be deflected a little bit to the right because the Earth is spinning in the northern hemisphere. And a lot of the time, that's going to cause the wind to go parallel to the isobars. So let's say this here we have, which I'll just draw in some little isobars for us. These are not very straight lines, but get the picture. We have our isobars here. Instead of the air going from, or the wind going from the high to the low, it's going to be deflected. It's going to go more or less parallel to the isobars. And this is called the Coriolis force. Don't worry about the little different names too much detail. This can be a little bit confusing. Sometimes physics does weird things when the Earth is spinning. There's also the concept that are called veering and backing. So veering is the name, the specific name that we give for when the wind is changing direction clockwise. So we have here the winds are going with the airplane, and then later on in the day, for example, now the winds are going a little bit more in a clockwise direction. Typically, throughout the day, as we go from the morning into the middle of the day, the sunny part of the day, essentially, the winds typically are going to veer and increase in speed. So during the day, if the winds are in the morning, we typically are going to be light. In the middle of the day, they're going to be stronger. And then in the evening, they'll be a little bit lighter again. Also, as you increase in altitude, so if you go from being on the ground to being at 5,000 feet, typically the winds are going to also veer and increase at the same time. So that's what veering is. Backing is the name that we give for when the wind changes direction counterclockwise, so the opposite of veering. Typically, they will back and decrease towards the end of the day, and as you descend in altitude, the winds will back and decrease. So, low-level winds, so winds at or near the surface of the Earth, don't always go in the direction you'd expect. So we can sort of do the sort of like theoretical physics aspect of how we'd expect the winds to go. But once we start getting close to the ground where there's trees and mountains and hills and buildings and oceans or not or lakes and rivers, all sorts of little local effects can cause a little bit of different effects. So winds on the surface can be a little bit different from what we'd expect because there's all sorts of stuff that's going to affect the wind. So there's lots of different factors going into which direction the wind goes. It can be a little bit complicated to determine. So we said before that the Coriolis force will cause the winds to go often roughly parallel to the isobars. However, and that's generally pretty true higher up in the atmosphere. So if you're up at 10, 30,000 feet, or 10,000, 20,000, 30,000 feet, that's probably pretty accurate. But once we get low to the ground, there's another factor to keep in mind, which is something called surface friction. So as air moves over the ground, friction between the air and the ground is going to start to play an effect, and that's going to cause it to do something just a little bit different from what it does higher in the atmosphere. So because there's friction between the air and the ground, it's going to slow down the movement of the air close to the ground. And because the air is moving a little bit less, there's going to be the effect of the Coriolis force is going to be a little bit less than it is higher up in the atmosphere. So instead of the air going completely parallel to the isobars and just going in circles here, it's going to be deflected just a little bit inwards towards the low pressure area and then just a little bit outwards away from the high pressure area. So it's going to be just a little bit different. And they say here, this typically doesn't go more than a couple of thousand feet in the air. So you can get a pretty big difference in wind speed and direction between the ground and 3,000 feet. You can see this pretty often in our are gliding operations where the winds on the ground can be relatively light, but then up at 3,000 feet, it's quite windy, which can be very noticeable with our gliders that don't fly particularly fast. And then we say, yeah, at 3,000 feet, the winds are parallel to the isobars and proportional to the pressure gradient, but lower to the ground, they will be inwards towards the low pressure and outwards away from the high pressure. All right, so next point to cover here, so we have squalls and gusts. So these are very similar sounding. The descriptions of them are very similar, but there's some important differences. So a gust is a rapid, regular fluctuation in the winds, essentially. So there's often a change in wind direction and or wind speed, and it's often associated with either mechanical turbulence or unequal heating of the earth. So, you're outside, the winds are at a certain speed, and for a couple seconds it gets a little bit windier, or for a couple seconds the wind direction changes fairly abruptly. Oh, I have a YouTube link that I'm supposed to play. Give me 1 sec. Let's see if this works. Or I'm supposed to have you play. Copy that. It is not copying correctly. Maybe we'll come back to that in a couple seconds if we've got time. A little quick YouTube video we will get back to. All right, so next we'll talk about squalls and how they're a little bit different from the gusts. So a squall is also a sudden increase in strength of the winds, but it's longer duration. So instead of being a couple seconds, think more in terms of like a couple minutes instead of a couple seconds. Often associated with a change in the wind direction as well. And these are often caused by either a cold front passing by or by a thunderstorm. So if you're outside, if we're flying and we see that the wind suddenly change directions 180 degrees over the course of a minute, that's a squall. And that's probably a sign that the weather is deteriorating in an interesting direction fairly quickly. Okay, so next is something called diurnal effects. This is a fancy name for the concept that throughout the day, the weather changes, in particular the winds. So diurnal essentially means over a day. As I mentioned before, in the middle of the day, the sunny parts of the day, especially when it's sunny and very, very sunny during the summer, that's when we're going to get stronger winds in the middle of the day. And then as the sun sets, the winds are going to decrease in speed and back again. Basically, the reason for this is, if we remember before, higher up in the atmosphere, typically the winds are stronger, and they also will veer. And when it's very sunny out, we're going to get vertical air. Air is going to start to rise and descend in different areas around the Earth. So we're going to get vertical mixing. So basically, the heating of the Earth is going to cause some winds that are higher up in the atmosphere to then come down to ground level. So we're going to get a little bit of those stronger winds from higher up in the atmosphere are going to be moved down to lower in the ground. So it's going to cause a bit of mixing. So the winds are going to get a little bit stronger on the ground, and they're going to typically veer and cause a little bit of gusting. So it is a diurnal variation. So during the day, the winds will tend to stronger and veer. At the end of the day, in the evening, the winds tend to get lighter and back. All right. We have more YouTube links. Why is this not cooperating for me? I would really like to share these. All right, I am just to play this. Have you? So it's a 2-minute and so video. Just had to play that, and we will resume in 2.5 minutes or 3 minutes. So. All right, so we saw that quick video. We'll just go through it on here. All right, so here we've got the land breeze first, which is going to happen at night. So at night, the ground is going to cool down faster than the water does because water tends to retain heat very well. So that we're going to get cold air over the land and warm air over the water. When we have this warm air, it's going to tend to rise and create a lower pressure area. So we've got high pressure here, low pressure here. So the air is going to tend to blow from the land to the sea, which is going to cause what's called the land breeze. Sea breeze is the opposite, which happens during the day. So during the day, the ground gets nice and hot quicker than the water does. So we'll get warm air here. Warm air is going to tend to rise. I'm going to have a low pressure. Air goes from the high pressure to the low pressure. And we're going to get the sea breeze. And these are really local effects. So it's going to happen in a little narrow area, but it's not going to be over a huge area of land once we're going further inland. It's really just along the water. This is going to happen. And a lot of these explanations are a little bit simplified and can be a little bit more complicated, but we're just going through the simple version. Next, we have two things that are similar concept, but instead of being with land and water, it's going to be with a hill or a mountain and the surrounding terrain. So these are called katabatic and anabatic winds. So first we have what's called a katabatic wind. So here in our little visual model, we have a mountain, which is a big chunk of rock surrounded by forest. And the big chunk of rock typically is going to be heated or cooled faster than the ground. If you think about sort of when if you're walking around outside during the summer, pavement is going to get very hot. Grass, not so much. It's going to tend to stay the same temperature. And then at night, the pavement's going to get very cold, but the grass is going to stay roughly the same temperature. The same little concept here in our little model where we have this big chunk of rock and all this grass or forest around it. So at night, our mountain or big chunk of rock is going to get cooled down faster than the surrounding area. So we're going to have cold air here. And this cold air is going to be denser than the warm air around it. So it's going to tend to sort of fall down the slope because it's heavier than everything around it. So it's going to be pushed downwards. And this is called a mountain breeze. The little phrase that sometimes people use to remember this is cats come home at night, or I'll use the other one that's used sometimes once we see the next one because it'll make a little bit more sense. So then we have the anabatic wind, which is the opposite. So during the day, the mountains get hotter than the air around it. So we have this warm air around the mountain. The warm air is going to be less dense, is going to start to flow up the hill. And then we will get this anabatic wind, also known as a valley breeze. So sometimes the phrase you see is, Anna went up the hill and brought the cat down. Whatever works for you, whatever helps you remember these things. I'm sure there's many different tricks you can use, but that is one of them that's often used to remember these kind of things. All right, if there's no questions, we will move on to air masses. I know we're covering a lot of topics very quickly, but there is just a lot of stuff. So a air mass is a large section of the troposphere with uniform properties of temperature and moisture in the horizontal. So it's a lot of words, but they are all fairly important. So it's an area of the troposphere, which remember is the lowest layer of the atmosphere. So area low to the ground relatively. And the temperature and the moisture are roughly the same over a large horizontal area. So let's say if we look at, for example, the area over, northwest region, for example, today it could be cold and dry, for example. And it's going to be talking about a very, very large area. So over, thousands of kilometers, thousands of miles, big area. We can talk briefly about the characteristics that are typically associated with cold and warm air masses. So typically, in a cold air mass, we'll have instability. So rising air currents will typically, because it's unstable, we'll have turbulence. Again, because it's unstable, we'll have good visibility because it's going to stop haze and smoke from really settling in very well. We'll have cumulus type clouds, showery precipitation, and we may have hail and thunderstorms in these cold air masses. In a warm air mass, we'll have stable air, which means the conditions will be smooth, but we may have poor visibility, stratus type clouds, and typically drizzle type precipitation will be associated. Now we'll talk in a little bit more about how the air masses are affected in a little bit, or are categorized, and how they affect us in a little bit more detail. I'll put the video on hold for a sec because it's maybe a little bit longer. Okay, so we've got, so like we said before, it's an area in the air mass where the moisture and temperature are roughly the same, and it's going to be, the air masses are affected by the area where they form. So an air mass that's coming from somewhere that's very cold and dry is going to be very cold and dry. So as you'd expect, the air is going to be like the place it's coming from. So these areas are called source regions, and I'll take the properties from where it comes from. Yeah, so Arctic air mass is going to be cold and dry most likely. Or if it's from the South Pacific, it'll be warm and moist. So we can use these to categorize our air masses in a little bit more detail. So we have the, we're going to basically categorize them using two letters. So one letter for the moisture content and one letter for the temperature. So the moisture can either be maritime for damp air or humid air, or it can be continental for dry air. So if the air mass forms over the water, it's probably going to be humid. If it forms over the land, it's probably going to be dry. In the temperature categories, we have Arctic, which is extremely cold, polar, which is cold, tropical, which is pretty warm, probably pretty warm, and equatorial, which is very warm from the equator. This is how we're going to categorize our air masses. So moving on. So the main source regions for the air masses that are going to affect North America. So it's either going to be Arctic, which is, from the North Pole down to the permafrost line, so very, very cold. Polar, let's say from the permafrost to where it's 10 degrees. And then tropical is below 30 degrees of latitude, which is quite a bit further south than where we are. So from where it's very warm. We are unlikely to get air masses from the equator here in Canada. And then, like we said before, our subcategories are maritime or continental. It's a bit of a repeat of what we said before. So we combine the source region with the subcategory. We get the two letters, and that'll give us the description of the air mass. So air mass can be continental Arctic, which means it formed in the Arctic over the land. So it's going to be cold and dry. It's going to form in the far north, and it's going to bring cold air with it. Then we have maritime Arctic, which is cold but moist. But really, the key thing to keep in mind here from this lesson is that it's categorized. They have the two categorizations, which tell us whether the air mass is humid or not, and how cold it is. Then maritime polar means that it is cool. So polar is a little bit less cold than Arctic, and maritime means it is humid. So formed over the North Atlantic, North Pacific Oceans, and it stays over the water, gets quite a bit of moisture. And then maritime tropical is going to form further south, and it's going to be warm air. Any questions on that? We'll see if we have time for that video, probably at the end. I'll maybe come back to it. A lot of videos to cover. Okay, so we'll talk about air mass modification. So basically, the air mass is formed somewhere in the source region. It takes on the characteristics of the source region, but then as it moves a really long distance, it can gradually start to be modified a little bit by the areas that it passes through. And it can be modified in varying amounts. So if it's passing very slowly through an area, it's going to be modified more because it's going to spend a long time in that area. So if an air mass spends a long time over the ocean, it's probably going to pick up a lot of moisture because it's being there for a long time. So the makeup of the surface is going to affect it. So if it's over the ocean for a long time, it's probably going to become more humid. If it's over the land, it's probably going to become less humid. And the temperature difference. So if it's a big difference, it's going to affect the air mass a little bit more. Here's just a random example. So you have this maritime polar air mass that's cool and moist. It goes over the mountains. As it rises, it expands, causes some rain. and then different things happen over as it moves through this area. So it's gonna, and as it goes through the mountains, it'll rain, it'll lose some moisture, and then eventually it'll be a little bit drier and keep moving along. But the exact details don't matter too much. General idea though, the air mass is modified by the land that it passes over. All right, so seasonal effects. So as we may have noticed, the weather at different times of the year tends to be a little bit different. So in North America, we'll typically have, in the summer, we'll have maritime polar, maritime Arctic, some maritime tropical and continental Arctic. So these are the air masses we'll see often during the summer. And in the winter, we'll often see maritime Arctic, maritime polar, and continental Arctic a little bit more frequently. So we'll get more warm air masses in the summer and more cold air masses in the winter, as it is colder in the winter. So a little picture of different things happening in North America. So we have continental Arctic in the north over the land, maritime polar over the water in the northern areas, continental polar in basically most of Canada, and then coming from the south we have continental tropic coming from the land, and then maritime from the water. So just this is generally more or less where the air comes from, just as a bit of a guideline here. So yeah, so these are the ones that we have typically in Canada. So this text doesn't mention continental polar, which it seems a little silly. All right, so quick confirmation. What are the two subcategories for air mass formation? There's two main ways we categorize them. So those are the things that we use. Those are the factors that we use to categorize our air masses. But there's an air mass can be either one thing or another thing. So the two subcategories can be, yeah. Nope, that's the other one. So the moisture content, the moisture content. So you can either describe it as, there's a name for when it has lots of moisture, and there's a name for when it has not a lot of moisture. What are those? We did continental or maritime. There we go. Good. There we go. Excellent. We got there in the end. So those are the two subcategories. Which air masses will we typically find in North America in the winter? We're getting a little bit more specific here. Continental Arctic, good. Yeah, that's one of them. Yeah, there we go. So we got maritime Arctic, maritime polar, continental Arctic. There we go. That's a complete list. Good. And what is an adiabatic wind? Yeah, so it's, yeah, during the day. Yeah, good. We got lots of answers. They're all correct. So during the day, warm air is going up the hill. Good. When will a land breeze happen and why? Almost. Very, very close. There's one small error in that answer. The answer was at night, the land cools faster. All that is correct. Sorry, no, what am I saying? It's entirely correct. I had a moment there. Sorry about that. So at night, the land cools faster. We get cold air over the land. So higher pressure over the land and lower pressure over the water. So air is going to go, wind is going to go from the land to the water. During the day, if the winds change direction from 120 degrees to 180 degrees, this would be an example of what phenomenon? Yeah, correct. So that is a veering. So the winds change, they're changing direction clockwise from 120 to 180. So that is veering. And what is the opposite of veering? Backing. Good. Good. And then last one. So which of the four, this is kind of similar to the previous question. So which air masses in Canada, so we answered previously what we see in the winter, and in the summer there's one more that we might see sometimes. So if you can just either give the full list or which one is the additional one that we might see in the summer. Yeah, maritime tropical, good. We will move on with the next lesson. So 40305, so fronts, frontal weather, and extreme weather. So we'll get to answer some or go circle back to some of the things that I mentioned earlier that we would come to on this lesson. So the main things we're going to cover, so a whole lot of teaching points again. So we've got front formation, warm fronts, cold fronts, stationary fronts, occluded fronts, upper fronts, how we see fronts on a weather map, thunderstorm development and hazards, aircraft icing, squalls, and tornadoes. So lots of things to cover. Let's get into it. So first of all, what is a front? So the front is the transition zone between two air masses. So let's say we have our continental polar air mass, and beside it we have a maritime tropical air mass. In between the two of them, there's going to be a little bit of a transition zone, and that's going to be our front. So in each air mass, the properties are roughly uniform, but in between them, there's a little bit of mixing during this transition. And this transition area, which is called the front, can move around and cause all sorts of interesting weather for us. So this is called the frontal zone, and they're going to move perpendicular to the frontal surface around the ground. So we've got our cold air here. I've got a warm air here. In between the two, we've got our mixing zone, which is basically where the front is. All right, so how does this form? So we've got essentially cold air and warm air don't really tend to mix that well. They'll mix just a little bit where they meet, but they're not going to the two air masses aren't going to merge into each other and cause a big super air mass. They're going to stay relatively separate, and the front will just form as they meet there. This area can be a little bit unstable because there's all sorts of interesting mixing happening between the two air masses, and often one of the air masses is going to be lifted a fair bit, which will cause some interesting weather. And a warm front is the retreating edge of a warm air mass. Anyways, we'll go through all the different types of fronts one at a time as we get there. That's just a quick picture of a warm front. So a warm front is when the cold air mass over here is retreating away from the warm air mass. Typically, that's the way it's always described. It's a front where the cold air is retreating, but you can also think about it as the warm air is moving towards the cold air. As the warm air advances towards the cold air is going to be more dense than the warm air. So it's going to be heavier. So what's typically going to happen is the cold air is going to stay on the bottom, and the warm air is going to move up the cold air. And because of a bunch of different factors, this is going to generally cause a gradual, gentle slope. So the warm air is just going to gradually, gently drift up this nice little ramp, essentially. And that's what the cold front is like. This can extend up to 500 miles ahead of a warm front, so that is very far. If the warm air is moist, we will get stratiform clouds or stratus-type clouds in a very specific order. So we're going to get cirrus, cirrostratus, altostratus, nimbostratus, and then stratus down here. So starting at the very far away, high up area, we're going to get cirrus. And then as we move closer towards the warm front, the clouds are going to get lower, and they're also going to get thicker and start to form more precipitation. So as the warm front approaches, we're going to get these thicker stratus-type clouds, and we're going to start to get precipitation and not so good weather in this area over here. Some people, to remember these different types of clouds in the order, they will use a mnemonic thing of C-cans. If that helps you, go for it. If it doesn't, ignore it. But that is one way that some people remember this. So for cirrus, cirrostratus, altostratus, nimbostratus, stratus. If this air is unstable, we can sometimes have embedded thunderstorms. So in the stratus or on the altostratus area, there could be a little bit of thunderstorm embedded inside of that, which can be a little bit dangerous if we don't realize that there's a thunderstorm hiding inside of a layer of cloud. A little bit of a diagram here of how many miles away with the different layers of clouds are. So here we got our cirrus clouds, hundreds of miles ahead. So the weather with the warm front, so as the warm front passes, the winds will tend to veer. So remember, that's changing direction clockwise. This is going to happen fairly gradually. Happen in the frontal surface, so really on the ground, and it'll be noticeable in the low levels as well. If you're flying through the warm front, you'll need to alter your course to the right, again, because the winds are veering. The temperature will gradually rise as the warm front passes. So because, let's say we're just sitting here on the ground, let's draw a little arrow. Remember, the front is moving towards the cold air, or the cold air is retreating. So if we are just here on the ground, we're going to be, as the front passes, we're going to go from being inside the cold air to being inside the warm air. So the temperature is going to increase, but it's going to be fairly gradual. These typically are going to be associated with low ceiling and stratus clouds and poor visibility, because again, we have in this area over here, we've got our stratus and our nimbostratus clouds. So we'll get poor visibility, we'll get drizzle. It can persist for some time because this is a slow moving front generally. Questions so far? Yeah, so the precipitation will typically begin in this altostratus region. So starting here in the altostratus, moving into the nimbostratus, and the stratus will get this precipitation, and then it'll be heavier as the front approaches. If it's very heavy, we can get thunderstorms, and there may be some turbulence, but less likely than with a warm front. But sometimes we can get these little embedded cumulonimbus. All right, so next, another little image. Now we have the cold front. So this is, it looks a little bit different. So remember, from the warm front, important thing to take away is that we have our gentle slope, and the warm air is gradually moving up that gentle slope. We'll get stable air, stratus type conditions. Moving on instead to the cold front. Cold front now we can see is a little bit of a different shape. And we'll go through that gradually. So the cold front is when the cold air mass is advancing. So the cold air is moving towards the warm air. And so as this mass of cold air overtakes the warm air, it's still colder, it's denser, and what it's going to do is it's going to push the warm air upwards fairly abruptly. So it's going to take this warm air mass and force it up into the air. That's going to cause this fairly steep shape at the front, and it can cause some very interesting weather. I don't want to go back too much because we do have a lot of things to cover. Just keep in mind that all of these slides should be uploaded and you'll have access to them afterwards. If we have time, maybe we can go back and answer questions, but we do have quite a lot to cover, so I don't want to go back. Oh, we have multiple requests. All right, okay. This one, or we want to go one more? Okay, I'll slow down a little bit, but I can't go back too much and I'll remember all of these are uploaded. You can go back on your own time as well. The recording should also be available. We do have quite a lot to cover, but all right. Moving on. So as the cold front passes, we get a bunch of different weather happening. So the winds will often shift quite quickly. Remember that this is a fairly abrupt phenomenon happening with our winds. So it can be a quick veering in the winds. You'll always have to alter your heading to the right as you're passing through. Sometimes it can be a little bit of a wind shift. Sometimes it can be a giant line of very strong thunderstorms, which we'll talk about later. Typically, the visibility will improve after it passes. And often there's going to be a narrow band of very strong showery precipitation. So remember that the warm front was this long line of gradual drizzle. The cold front, think about just like a line of thunder showers, essentially. And it can be quite turbulent. The temperature will drop as the front passes. It can take a couple hours. As the front approaches, the pressure will drop and then it will rise again once the front passes. So in the area just before the front, we can get this little low pressure zone, along with all the bad weather of the front. But then after that, the pressure will increase again. And how bad the frontal weather is going to be is going to depend on the moisture content and the stability. So if it's very moist and unstable, you get very strong thunderstorms. How fast it's moving. If it's moving quickly, it's typically going to be a narrow band of about 50 miles. And if it's moving very slowly, flight can be affected for hours or really even often days for a slow moving warm front. Next, we have a stationary front. This one is not very much is happening. We have our cold air, we have our warm air, and neither of them is advancing or retreating. They're just kind of staying stationary, hanging out, nothing's happening. After a few days, it can either dissipate or it can start moving in either direction and become either a warm front or a cold front. So we have our stationary front here. So we just have this, nope, that is not a stationary front. That is an occluded front. Sorry about that. So there's no image for the stationary front. So next we have occluded fronts. So these occluded fronts are fronts where we have 3 air masses now. So we've got, usually they describe them as cold, cool, which is a little bit warmer than cold, and warm. Here we have 2 different cold air masses. Be a little bit, be described in different ways. Now we have 3 little sections. And basically this can happen when one front catches up to another front. So here, for example, we have a cold front, which is moving pretty quickly. I guess I'll add in an arrow here. cold front moving quickly and a warm front that's moving kind of slowly. So the cold front catches up with a warm front, and then it's going to push all this warm air up into the completely off the ground up into the air, which is what's the occlusion is what it's called. And because we like giving extra names to things for aviation, it's called a trough of warm air aloft, or a trowel is this air here, that's this warm air that's being pushed up into the air. And that's just the name we called it. The weather that happens with these trowels varies quite a bit, but it's typically basically we have a cold front, we have a warm front, we shove them together, so we're going to get a little bit of a mix of those two things. So we'll get a little bit of showers, a little bit of stratus clouds, a little bit of cumulus clouds, a bit of a mix of the two of them. All right, next, a little bit of a weird one is something called an upper front. So this is important, is not an occlusion. So occlusion was the front where we have an air mass that's being pushed up into the air, but that is not an upper front. An upper front is essentially when there's a bit of air that's trapped in an area low to the ground. So for example, in an upper cold front, we have a cold front that is passing over a valley. So there's a little valley, and in that valley, there's some trapped cold air. The cold air front, because it's not quite as dense as this super cold air in the valley, it's not going to push it up into the air, it's just going to pass right over it. And then similarly, an upper warm front is when a warm front is passing over cold air in a valley. We don't have too much to worry about these. Typically, the weather associated with these is going to be the weather of the front that's passing by. So if a warm front is passing by, we're going to get all the weather and precipitation of that warm front, even when it's an upper warm front. All right, so what these will look like on a weather map, if we have a warm front, it's going to be these red half circles on a red line. If you want to say, think of a warm rising sun, if that helps, go for it. Cold front, little blue triangles, think of icicles if that works for you. An occluded front is triangles and half circles on the same side of the line. I have seen them before as being blue and red. I think pink may have replaced that. A stationary or a quasi-stationary front is triangles and half circles on opposite sides like this. And then the upper fronts are these but hollow. And the triangles or the circles indicate the direction of the front. So these ones are all moving upwards on the screen. So they're all moving. Oh, sorry. And they're all moving that way. The quasi-stationary front, they're pointing in opposite directions. Which way is the stationary front moving? It's a silly question. Stationary front is not moving. All right, so moving on to thunderstorms. I have another video for you guys, for all of you, that I have this time saved ahead of time. It's 3 minutes. Copy that in here, watch that, and we will resume after the video. All right, so we will resume. Start talking about thunderstorms. So for a thunderstorm to form, we need three different things. We need to have unstable air, some form of lifting agent. So these are going to usually be either convection, frontal, or orographic. So I believe this was covered in a previous week, what lifting agents were. If not, let me know and I can go back to it. And high moisture content. These are the things that we will need for a thunderstorm to form. So they go through three different stages. So first we have the cumulus stage. So we have a cumulus cloud in unstable conditions with rising air conditions that are good for vertical development. This is going to, and updrafts will start to form in this thunderstorm cell. There is no precipitation during the cumulus stage. And in this cloud, it's going to be normally warmer than the air around it, and it's going to keep growing and rising. During the mature stage, this is when we start to get precipitation. We start to have downdrafts, so descending air in the center of the cloud, which can be quite fast, which can be very bad if you're flying through that area. So if we're descending at 2,500 feet per minute, that's a lot of descending, which could be very bad for you and your airplane. The updrafts is they can reach up to 6,000 feet per minute, which is a lot. That's they're rising at 60 miles an hour, 100 kilometers an hour. That's a very, very strong rising air. Precipitation starts. Typically, this stage is really only 15 to 20 minutes. So strong thunderstorms, they burn out fairly quickly, can last up to an hour, but it's mostly in the 15 to 20 minute range. And then the last stage, it will start to dissipate. The whole cell will start to create downdrafts, and it will stop the precipitation, start to lose energy, and that's when we sort of see it spreading out and making that distinctive anvil shape sometimes. So if we move on, here we see our cumulus stage. It's all rising, no precipitation. It starts to grow into this big, from a little cumulus cloud into a towering cumulus, then eventually into a cumulonimbus or a thunderstorm. In the mature stage, we start to have some downdrafts in the center area, but still some updrafts around it. Precipitation forms underneath, and they can get very, very tall. And then during the dissipating stage, it's all downdrafts, and it's slowly, slowly fading away. We will move on to the thunderstorm hazards. There's no questions. So the weather associated with thunderstorms. Yeah, so basically there's a couple different types of thunderstorms. You can either have an air mass thunderstorm, which is when they are separate cells or little clusters of cells. So there's, we have a little thunderstorm over here, a thunderstorm over here, a thunderstorm over here on the map, but they're fairly isolated. Or we can have a frontal thunderstorm, which is when there's a giant line of thunderstorms associated with usually with a cold front, but sometimes a warm front. All of these fronts can have fairly strong wind shear, which is when the winds are changing direction and speed fairly quickly. And as the thunderstorm is happening, a lot of time there's strong downdrafts that can often be well ahead of the thunderstorm, and the winds can change directions quite a lot. So if we're outside and we see that it's a nice sunny day, and then all of a sudden the winds change direction 180 degrees and get super strong, that's probably a sign that we should consider packing things up for the day, essentially. So our thunderstorm hazards. So the downdrafts, like we said before, they're quite strong and they can be hazardous to fly through. So if we're flying through 6,000 feet per second of descending winds, that's not a place you want to be flying around. That's a place where essentially flight is unlikely to be possible. So it would be a very bad time to go fly through there. The winds can rapidly change direction, very strong wind shear can be quite bad. So there's this large area of descending air that's often called a macro burst, which is a couple miles wide, which can last for a few minutes or for up to 20 minutes. And sometimes there's a very, very small little narrow area where the winds descend for a very short period of time, which is called a microburst. All of these are places you don't want to be flying. Put a little bit of a diagram here about different areas. I wouldn't worry too much about these numbers in here, but in general, it's just flying through a microburst is a very bad time. Would not recommend. Lightning is a common thing that happens in thunderstorms because of the electric charges. It's not good for flying, can cause difficulty seeing, can cause problems for electrical instruments and other equipment. It's not ideal. Other hazards. So we've got our turbulence. That can be very severe. It can be things that can cause loss of control. It can cause, it can essentially just break your airplane. Yeah, even if you're just flying along normally, it can be very bad. Lightning strikes we talked about before. And hail, so usually is in the higher range, but can often be found lower, and can cause quite severe structural damage to your aircraft. So hail is something we often see in big thunderstorms in the summer, which can cause these large hailstones, which are very bad. So that is that. Additional hazards, so icing. So if we're flying through an area where there is icing, so essentially icing conditions is when, as you're flying, ice will start to just accumulate on your airplane. So on all the different surfaces of your airplane, ice is going to start to just build up and create a layer on there. We'll talk about that more shortly, but this is very bad for continued flight. Pressure changes. Remember that our aircraft instruments often rely on the atmospheric pressure, and because there are large changes that can cause unreliable altimeter readings. The winds can change a lot, strong gusts. All of these can cause problems. Rain is in very bad, if it's very severe, it can start to become hazardous as well. So it can be difficult to see, can cause damage to the aircraft, can cause issues with our instruments. If the windshield of the aircraft is wet, it causes something called refraction error, which makes it difficult to judge your glide slope. And lastly, hydroplaning. So if the runway is flooded, your braking abilities can be fairly limited. We'll see that on the runways. We'll also see that on our grass strips for the gliders, where if it's very wet, it can be difficult to brake, and the aircraft tends to just want to slide around. So with all those hazards in mind, we'll talk about not flying in thunderstorms. So these are some general principles of avoiding thunderstorms. So first of all is don't fly through a thunderstorm, which is, with all the hazards we just mentioned, should be pretty straightforward. We should also avoid taking off or landing near the thunderstorm. So this can sometimes cause some confusion on some of the questions. If the question is, there's a thunderstorm nearby, what should you do? Immediately taking off or landing is often going to be the incorrect answer on that question, because you should instead try to fly away from the thunderstorm and try to land somewhere safely. That's assuming you're in an airplane with an engine that can actually go somewhere else. If you're in a glider, you're probably limited to, you're probably going to have to land wherever you're going to land. Also, don't fly under the thunderstorm. Remember, those big, strong microbursts and macrobursts can be bad. And if you see turbulence, you should reduce to your aircraft's maneuvering speed, so that you'll have less forces on the aircraft. If you need to fly around a thunderstorm, you should stay at least 10 to 15 miles away, and you should stay on the right side of the thunderstorm. So with the thunderstorm on your left side. This because it's a low pressure area typically. The thunderstorm will have air that circulates counterclockwise. So if you're on the right side of the thunderstorm, you'll have a tailwind behind you, which will help you fly around it. If you must, for some reason, fly through the thunderstorm, you should hold a constant heading, reduce the maneuvering speed, try to avoid the icing, try to avoid the areas which look dark and very lightning filled and scary. Try to go straight through it as opposed to across it. But really, we should just don't fly through thunderstorms is a general pretty good rule. So questions about thunderstorms? If not, we will move on to icing. All right, so icing, like we said before, is ice forming on our aircraft surfaces. This is very bad. It causes lots and lots of problems for airplanes. So we can start to reduce the amount of thrust. It will increase the weight because more stuff is on our plane, so the plane is now heavier. It's going to decrease drag and decrease or increase the drag and decrease our lift. So there's going to be all sorts of weird irregular shapes forming on our airplane, which are going to disrupt the lift and increase the drag. It can cause quite a lot of negative effects on our airplane. So this icing typically is going to occur as we're flying through clouds, in freezing rain or in freezing drizzle. And so our stall speed is going to go up and everything is just not going to go very well. Can also restrict some of our controls. If it's very severe, we could have our controls get locked up. We could lose instruments if, for example, our pitot tube ices up. If our windscreen is covered in ice, we can't see anymore. All of these things are not good for flying. So icing is bad. We'll move on to the specific types of icing. So first we have something called frozen dew. So this is this little clear, little crystalline frost that covers the surface of the aircraft. And so this happens typically overnight or in the early morning, where at night the air gets cooled down to the dew point. So what happens is dew will form on the airplane. So if we think of when you go outside in the morning and the grass is wet, that's dew, but then the dew forms in your airplane and then gradually freezes into ice. So this is when it's not super cold, which is an important distinction to keep things separate from the next type of icing we're talking about. So important to keep in mind for frozen dew is that water vapor condenses into dew on an airplane, and then over time it will cool down more and then start to freeze. Like any ice, we got to remove it before we go flying. Next, we have hoarfrost, which is another type of ice, which is going to happen when it's very cold out, and when the dew point is cold enough that instead of the water vapor turning into dew and then freezing, it's going to go directly into ice on the surface of our aircraft. And it's usually on cold, clear nights, and it's instead of forming as dew and then freezing, it's appearing directly as ice on our airplane. Yeah, and think if you go outside and the grass is all a little bit frozen looking and white and frosty, that's what we're talking about there. Our next two types of ice, or the last two we're going to talk about, are rime icing and clear ice. So rime ice is what happens when there's lots of super cooled water droplets in the air, and because these water droplets are super cooled, they are below the freezing temperature, but they're just looking for something to freeze onto. So the second they come into contact with their airplane, they're going to instantly freeze, and because they're freezing instantly, they're going to make irregular shapes on the airplane. So they're just going to, this little drop of water is going to freeze on the plane. It's going to instantly freeze on the plane in like a weird droplet shape. That's going to cause it to be opaque. So instead of being clear ice, it's going to be like a little bit white colored. It's going to make all sorts of weird lumps on our airplane. The alternative is clear ice, which is going to happen as the water droplets freeze a little bit more slowly. So water droplets appear on the plane, they spread out a little bit, and then gradually freeze to make a solid, thick layer of clear, transparent ice. So these are the two more severe types of icing that we get usually in flight. Sometimes we're going to mix of both. Sometimes we'll get just one or the other, but rime ice is the slightly opaque, irregular type of ice. Clear ice is the clear, regular layer of ice. All right, squall lines. So that's icing. Move on to, I believe, one of our later topics. So a squall line is what happens when we have a cold front, and all along the whole length of the cold front, we have this giant line of thunderstorms. So we've got our warm air, we've got a cold air, and then in between the two, there's just this big wall of thunderstorms. And this is what happens when we have a fast cold front with a big unstable warm air mass. So it's just in front of our front, we get this big wall of thunderstorms. That's a squall line. A tornado, I think we probably all know what a tornado is these circular funnels of very fast, very strong air, shaped like a funnel. They're pretty small. They move around very fast. Very strong winds. Don't fly into tornadoes. You'll have a bad time. All right, any questions so far? All right, we'll move on to our confirmation. So, what are the 3 stages of a thunderstorm? Yeah, cumulus, mature, and dissipating. Good. All right, good, cool. Next, list the forms of icing and provide a short description. So even really just a couple words. There's 4 different types. So hoarfrost is sublimating directly into ice. Yeah. Description is right, but that is rime ice for the description we got there for immediately freezing into regular shapes. Got 2 more. So we got clear ice, which is the thin layer of regular ice, and we've also got frozen dew, which is when dew appears on our object and then it gradually freezes into ice. Squall line is that long line of thunderstorms with a cold front. We just saw that a minute ago, so skip that one. We're in a little bit of a, yeah, there we go, clear ice. All right, next, what weather is associated with a thunderstorm? There's a lot of different characteristics. I'm not going to ask you guys to name all of them, but if we can get some of them, that would be good. We got downdrafts, we got unstable air, good. Yep. I'll wait for, let's say, 2 more. Lightning, good. One more. High moisture, sure. It's not really one of the weather. Yeah, hail, precipitation, rain, good. So the list of things, we got the gusts, we got downdrafts, we got microbursts, lightning, icing, hail. Yeah, there we go. Good. Thunderstorm hazards are essentially all of those same things are essentially hazards. So I don't want to. Yeah, there we go. Good. How should you avoid a thunderstorm? Just a couple of those. A couple of those tips we just said before. So first of all, what should we not do? Yeah, so if we do need to fly around them, fly around to the right. Ideally, though, yeah, don't fly. Yeah, don't take off or land near them. Don't fly under them. Don't fly near them. If you must fly near one, go around to the right. And if it's turbulent, fly your maneuvering speed. Good. And what are the requirements for thunderstorms to form? So we need three things for a thunderstorm to form. Unstable air, lifting, high moisture. Good. All right. We'll do the last one. All right. What's the difference between a cold front and a warm front? Okay. Yeah, that is a good answer. In which way is are the air masses moving in each front? But yeah, that answer is entirely correct. So where is the cold air going in each one? So cold air front, the cold air is advancing. A warm front, the cold air is retreating. So we'll get started with our last lesson, which is going to talk about weather reports, which are and forecasts, which are METARs and TAFs. So we will get into it. So we're going to go through an overview of what weather reports are, automated weather observation, and then something called routine weather reports, or METARs, TAFs, which are terminal area forecasts, and then how to read these different types of forecasts. All right, so aviation weather report. So just a bit of an overview. So basically, at certain specified aerodromes in Canada and the USA, they take weather observations every hour, sometimes more often, but ideally at least once an hour. This can either be done by an observer. So there's a person who has this whatever qualification training they need to correctly record the weather, or by some sort of automated station, which will just automatically take a bunch of measurements and write these things down. We can find these online. This screenshot is actually out of date. The web pages have been changed, but it can all be found online on the NAV Canada website. And it'll give us all this information online. So something called AWOS, which is an automated weather observation station. So these are these fancy electronic devices that will automatically capture things and then publish the weather reports online, so that we can easily check the weather from remotely via the internet. So there's two types. It can either be the full AWOS, which is all the sensors, which will measure, a bunch of different things, the temperature, the clouds, different types of clouds, all sorts of things. And then some airports will have a more limited station, which is called an LWIS, which is it will just measure the winds, the altimeter, the temperature, and the dew point, which are the main things you need to go flying. But sometimes it's good to have the full forecast, and it just depends on how many sensors that they have at the station. Both of them can have equipment so that you can actually check the weather at the airport by either over the radio or by telephone, where if you call the number, it will just tell you the current weather, or over the radio will tell you the current weather at the airport. Can be a little bit iffy in terms of actually working, but they do exist. Most of the time, though, if you are not currently in flight, most of the time what people are going to do to get the weather is they're going to go onto the Nav Canada website and check the METARs on the TAFs. Or if you are currently in flight, you can contact the nearest tower or Unicom, and they can give you the current weather at that airport. But those automated systems do exist. So we're going to move on to the meat of the lesson, which is how to decode weather reports and forecasts. And it's really important that we know the difference between these two things. All right, so a METAR stands for a meteorological aerodrome report. And it's really important that we remember that a METAR is a observation of the current weather at an airport. So it's someone or a computer, but you could really just think about it of someone at the airport looked around, measured the temperature, measured where the clouds were, and said, yep, this is the weather right now at 8 o'clock at the Toronto airport. This is what the weather is. And it's coded using a certain ICAO standards that everyone around the world knows how to read them. They're typically reported hourly. And again, super important, they are only valid at the time of issue. So if I make a METAR at 8 o'clock, the METAR is valid for this airport at 8 o'clock. It is no longer valid at 8:05. It's no longer valid at 8:30. That's really just it's instant. It's just valid for that instant, just saying, yep, this is the weather where I am. And it's generally within three kilometers of the observing site. The time is given in Zulu or UTC, so the time, the universal time coordinate, so the Greenwich time. Winds are given in degrees true. Cloud height is given in feet above ground level. Visibility is in statute miles. Temperature is in degrees Celsius. The altimeter setting, when it's given, is given in inches of mercury. We've got to remember all of these units is quite important for the METARs. So let's get started on how to decode METARs. Sometimes, so most of the time, the METAR will start with the letters METAR. Sometimes, though, it'll say SPECI at the start. What that means is, so normally the METARs are every hour on the hour. But sometimes if the weather changes a lot, they might decide to put it as SPECI. So let's say the weather was super nice, there was no clouds, nothing, and all of a sudden it's all thunderstorms everywhere. Well, maybe the observer will decide, all right, the weather's changed a lot, I'm going to put it as SPECI. I'm going to make a special observation at an unscheduled time and put one of those out. But normally it'll just say METAR at the start. If they had to make a correction, they will also have these other special letters. So CCA for the first correction, CCB for the third correction, etc. So for example, if it says METAR CYWG CCCA, that means it's a METAR for CYWG airport. I don't know where that is. for the 13th day at 20 Zulu clock, which is the time, and this is the first correction. And we'll go through how to read these in detail. Winnipeg, yes, good to know. Oh yeah, it's here on the next page. So anyway, so these are these unique identifier codes for airports. So every airport has an ICAO code. In Canada, they all start with a C. With a Y, if it has a Y or a Z, that means that the reporting station is at an airport. So CYWG is at Winnipeg, this one's at Brandon, etc. If it has a W, it is not at an airport. So this one here, YWLM, is just not at an airport. And if it's a U, it is at a beacon, like a radio navigation aid, like a VOR or something. So these are some airport codes. You don't need to memorize all of these for different airports. You just need to know that that's what those are. All right, moving on to how to read an airport code. And I hope you guys can all read that text because it is quite small. We'll see how that works. All right, so we'll go through bit by bit. So we start with CWIG. So this is for the Winnipeg airport. The next block is always going to be the day and time. So 30/2000Z means it's on the 30th day of the month at 2000 Zulu. So 8 p.m. In Universal Coordinator time. Then the next block is the winds. So these are going to be, just going to get this. Yeah, so this is the observation date and time. Then we have the winds, other weather. Actually, I think we may go through this. Hold on 1 second. Yeah, so then we'll go through the next is the surface winds. So the surface wind, they basically take a look at the average winds over the 2 minutes before the observation. And then we're going to give the wind direction and wind speed. So first we get the direction. So here it says 240. It means the winds are coming from 240 degrees. Then the next 2 digits, so the last 2 digits, are the wind speed in knots. So 24010 means the winds are 10 knots in wind speed. Sometimes they will have a VRB, and that will mean that the wind speed and direction is variable. So it might be VRB 03, which is that the winds are variable 3 knots or less, change in direction. Sometimes, this one is very uncommon, I haven't really seen this very much, it might have something like 060V130, which means that the winds are varying from 060 to 130. So it's in this whole range. Winds are varying between those two. And if the winds are entirely calm, it will be 0000 KT. If the winds are gusty, so that if it's gusting more than 5 knots above the average wind speed, and it's more than 15 knots, they will report the gusts, and they will do this by adding on a G and then 2 more digits. So for example here, 30015G25. What that means is the winds are coming from 300 degrees. Remember, that's degrees true. And there are 15 knots gusting to 25 knots. So the average is 15, but sometimes it goes all the way up to 25. All right, next we have the prevailing visibility. So this is how far can you see in most of the area around the observing site. And they will give it in statute miles in North America. They give it in meters, kilometer, either one in other places, but North America is statute miles. And sometimes they'll give it as a fraction. If it's less than 1 whole mile, they give it as a fraction, typically. and sometimes up to 3, but it can be very, very specific sometimes. So for example, here we've got, which may be difficult to see over here, we've got, so we go through here, we see our wind, and the next thing here is 2 SM. So the prevailing visibility is 2 statute miles, and sometimes they will give extra remarks at the end. So here they say remark, that is hard to see. Remarks visibility northeast 1 statute mile. Less common, but really we do need to, the main visibility is right after the winds most of the time. I know we've got a lot to go through here, but there's a lot of stuff. All right, next we have the runway visual range. So this is if you are standing on the end of the runway, how far down the runway you can see. And they really only report this when it's not good. So it's when the visibility is 1 mile or less, which is quite bad. Is ST8. We'll get to that actually. But it is the second one. But we will get that at the end. Yeah, so the visibility is 1 mile or less, or the runway visual range is 6,000 feet or less. And the grouping, they will put R, then the runway number, and then if they need to, they will put a L, R, or C if there's multiple runways in the same direction. So for example, runway 36 left, then they'll put a slash, and then they'll put the visual range in hundreds of feet. And then they'll put feet, and then after that they'll put a slash, and they will either put whether they will indicate whether the trend, so what's happening to the runway visual range, whether it's a D, meaning it's a downward trend, so the runway visual range is getting worse, and a U for an upward trend, meaning it's getting better, or an N, meaning it's not really changing. For example, here we see R36L / 4,000 feet / D. So that means the runway visual range on runway 36 left is 4,000 feet, and it is deteriorating. It's getting worse. So that is the RVR. All right, next is the present weather. So this is if there's any weather that's happening. There's rain, there's snow, there's hail, there's volcanic ash. There are codes for all of these things. There's lots and lots of codes. These present weather can also be modified by having either a minus for light or a plus for heavy. And if there's no anything, it's just moderate. Sometimes they will also have a VC, which means it's nearby, but it's not at the station. So for example, if there's tornadoes in the area of the airport, but there's not a tornado on the airport, it still might be good to know that there are tornadoes near the airport. So they would probably write, tornadoes. I don't remember what a tornado is, but VC. For example, yeah, VCSH, or showers in the vicinity, or VCFC, meaning funnel clouds in the vicinity. Now, there's a lot of different codes for different things. And they can also, like I said, we can have light, moderate, or heavy. We can have a vicinity. Sometimes they will also have these other descriptors. So they can have freezing or blowing or drifting or partial, all these kind of things that apply to the same thing. And then we have our different things. We can have drizzle, we can have rain, snow, snow pellets, ice crystals, ice pellets, hail, small hail, mist, fog, smoke, haze, dust, sand, volcanic ash. All of these things, tornado is plus FC, good to know. So all of these things. There's a lot of codes. Unfortunately, many of them we may just have to remember what they are. Some of them are a kind of self-explanatory, like we see RA or we see SN, we can probably guess. Others are sometimes a little bit harder to guess what they are. Usually we won't see any super weird ones, but never know. So do we have some the obscuring phenomena? We talked about that before. So haze, sand, dust, mist, fog, all of these things exist as possible things that we can see on a weather report. So next we have the sky condition. So we're going to basically describe how many clouds there are and how high up the clouds are. The way we do that is we divide up the sky into imaginary segments that are called octas, and we basically divide up the sky into 8 little imaginary pizza slices, and we estimate roughly how much of the sky is filled with clouds. So if it's clear, there's no clouds. If it's few, there's a little bit of cloud to up to 2/8, 2 out of the 8 octas, so up to a quarter of the sky. Scattered is from 3/8 up to 4/8. Broken is from 5/8 to 7/8, or really even to just less than the whole sky is full of clouds. And then overcast is the whole sky is a solid layer of cloud, overcast. And they will be given in these abbreviations. So SKC, few, scattered, broken, overcast, all those things. Sometimes they will just write CAV-OK, which is just ceiling and visibility are okay. So it replaces both the visibility and the ceiling. And this is when the visibility is better than 10 kilometers or probably 6 statute miles. No clouds below 5,000 feet. No cumulus or TCUs. No rain, thunderstorms. Basically, if the weather's good, they might just put CAV-OK. Not super common, but they could do that. The layer height is how high are the clouds for a specific layer of cloud. We report it in hundreds of feet. So 001 means 100 feet, 020 means 2,000 feet, and 300 is 3,000 feet. I know there's a lot of stuff. We'll get through some full examples in a little bit. So for example, here it says, if it says OVC 030, that means overcast 3,000 feet. Next, we have the vertical visibility, only given sometimes, and this is when essentially if you look up, it's not a cloud, it's just there's like stuff that makes it hard to see the sky, like you're in fog or mist or something like that. Those are going to report basically how high up can you see. So here will be VV004 is vertical visibility 400 feet. After that, we have the temperature and dew point. So they will give us the observed values for the temperature and the dew point. So for example, if we see 0.3, that means 3 degrees of the temperature, and M is for minus. So -1. So the temperature is 3 degrees, the dew point is -1 degrees. And then we have the altimeter setting. So the altimeter setting is the number you got to set on your altimeter to make the altimeter report correctly. So if it says A2992, that's 29.92 inches of mercury. So there's that. There's a lot of stuff in the chart. We'll get to some examples shortly. We're almost done. They may also report other things as recent weather if some special things have been happening recently that would make things interesting. Very specific details. Some things can be a little bit different sometimes. So if there's something both in the present weather and in the previous ones, they can report it in a couple different ways. Don't want to get too much into the weeds there because we do have quite a bit to cover and want to get to some examples. All right. So if there is wind shear, this is typically something that's been observed by the pilots or by measuring it in the air in the tower or something, they'll indicate the wind shear. They'll usually indicate that it was observed on a specific runway, or they can put that it was observed on all runways. So if it's WS runway 20 right, is that someone encountered wind shear on 20 right. And then at the end we have the remarks. So these are other things. So they'll give sometimes the specific type of cloud and how many octaves there are, which is the question we got earlier. So if it says ST8, that means there are 8 octaves of stratus clouds. They will often sometimes give the sea level pressure in hectopascals. Now this one, the sea level pressure can be quite confusing because they only give the last 2 digit or last 3 digits of the number. So for example, they say SLP 134. They are giving us the sea level pressure, telling us the sea level pressure is 1013.4. The thing that can make this confusing is they give us the last 3 digits, and before those last 3 digits, there can either be a 9 or there can be a 10. We have to use our judgment to know which one of those it is. The way that we do that is basically we want to look at the sea level pressure will basically always be around 1,000. If it's not around 1,000, things have gotten real weird. So if we see 134, we need to think about, okay, which one of those is it likely to be? Is it going to be 913 or is it going to be 1,013? And we're going to look at the one where it's going to be closest. We're going to pick the one that's closest to 1,000. So we're going to pick 1,013. If we see it's 934, it's going to be 993.4. That can be often confusing because it's written in a kind of confusing way, but that's just the way it is. And then if there's anything else that's interesting or significant, that you can put it there. The remarks, sometimes there's not necessarily always a specific way of coding it. They kind of just cut out letters. You got to look at it and try to do your best to decipher what they're writing. So here, for example, is remark, stratus fractus 5 octaves, and nimbus stratus with 3 octaves, and then sea level pressure 913, or sorry, 1013.4. Whoops, I will erase that writing so we can actually read that. Another example is stratocumulus 3 octaves and 0 octaves is cirrus. They rarely will write that, but they might put that. And sea level pressure 999.2. Normally it should be SLP, not SPL. All right, so these are different types of cloud abbreviations. They all exist. It's possible that we get a new of these. All right, remarks. Sometimes they will put partial obscurements if they're just saying that there's fog in some parts of the area or something else like that. They can put some little remarks like that. They say, sky clear in the clouds, and then at the remarks they'll say there's fog in 5 octaves of the area. All right, so that's the METARs. Now we'll move on to our TAFs, and then at the end we'll get to some examples once we get there. The good news, though, is that almost all of the stuff we learned for the METARs is going to be applicable to the TAF. So all the abbreviations and stuff will be very similar. So a TAF is a aerodrome forecast. Important to remember the difference. So a METAR was, this is what the weather is right now at the airport, at the aerodrome. A TAF is a forecast for what we think the weather is going to be over the next 24 hours around the airport. So we're going to write down what we expect for the key weather factors around the airport. They're typically issued 4 times a day, roughly 20 minutes prior to the period that they're going to cover. The validity period is often confusing. So they are normally valid for 24 hours. However, as soon as the next TAF comes out, it replaces the old TAF. So sometimes people get confused and they think that because they're issued 4 times a day, every 6 hours of the validity period is 6 hours. That is incorrect and can often be gotten wrong on an exam. So the validity period of a TAF is usually 24 hours. That's valid from when it's issued until the period ends or until the next one comes out. And remember, this is a forecast. It's telling us what we think the weather is going to be for the next day. All right, so how do we read a TAF? So the first thing, same 4-letter ICAO code as the METARs. Date and time. This time the date and time is given in, for being issued is the same, but the validity period is a little bit different. So CYVR for Vancouver, 1/8, so it's on the 18th, and it's issued at 1640 Zulu. That's given it at that time. Next, we have the validity period. So here it'll be the day and the hour for the start until the day for the day, and then the day and the hour for the end. So this TAF is valid from on the 18th, 1700 hours, so 1700 o'clock, until the 19th, 17 hours. So it's valid from the 18th at 1700 to the 19th at 1700. So it's valid for 24 hours or until it's replaced. Sometimes they can be amended if there's been a big change, but it's not super common, but it can happen. If that happens, it will be, they'll put AMD for amendment. For example, here. The wind will be given exactly the same as the METAR. So most of the time, it'll be exactly the same. Sometimes we'll put a wind shear at an altitude, but most of the time it'll just be something like 250, 50 knots. When there is wind shear, they will put the altitude that it's visible up to. So wind shear is expected up until 1,100 feet. And then the winds at that altitude are 200 at 50 knots, which is quite strong. Visibility is given in miles and sometimes fractions, except that when the visibility is expected to be more than 6 miles, they will just put P6SM. So if they think it's going to be 10 or 20 or 100, they'll just put P6. So for example, here we've got TAF, Winnipeg. It's issued on the 12th at 1140. It's valid from the 12th at 11 o'clock until the 13th at 11 o'clock. The winds are expected to be from 240, 20, gusting 35, visibility more than 6 statute miles. So all of that stuff is basically the same as the METAR. Now we'll move into the new things. And all of the stuff here looks the same as the METAR, but there's just this extra little FM that we got to think about. Yeah, all of the abbreviations are the same. All of the intensity, all that stuff is all used as expected. So they could put light rain, heavy rain, thunderstorms, all that stuff, sky condition, sky clear, overcast, altitudes, all that stuff exactly the same. Sometimes they put NSW for no significant weather. Really, the next interesting thing, though, is how, because the weather in this 24-hour block is unlikely to be the same the whole time, they have to give us the weather, what the weather is going to be at the start and what it's going to be later, and that's when things get a little bit more interesting. So they divide it into little periods, and then they will basically list, okay, the weather is going to do this and then it's going to do this, and later it's going to do this, and then there's some other little details like that. So FM means from, and what that means is it's a permanent change in the weather that's going to happen fairly rapidly. So let's say at the start you said there's no clouds. Now you're going to say from this time there's going to be overcast clouds, which means at that time roughly the cloud will suddenly become overcast. For example, let's say from 10:040, that means we're expecting on the 10th at 4 o'clock a bunch of stuff's going to happen. Since this is a permanent change, all of the weather elements that are earlier in the forecast are now replaced. So for example, we look at this here, we see 240, 15 gusting 25, 3 statute miles, light rain showers, scattered at 1,500 feet, overcast at 4,000 feet. So that's the weather we expect at the start of the TAF, for example. Then we see from this time, so then starting at 4 o'clock, we expect all of this stuff to happen. So now the winds are going to be 200 at 10, so the winds got lighter, visibility got better to now more than 6 miles, scattered at 2,000 feet, overcast at 3,000 feet. And then maybe later there's a from 10 o'clock, then there's a from 1,700 hours, whatever. So we look at all the different blocks and look at the weather that's happening in each of them. Next, so instead of from, sometimes it says becoming, or be like becoming. This means that there's going to be a permanent change, but it's going to be a little bit more gradual. And they sometimes will only indicate which conditions are going to change. So if the winds are going to stay the same, the clouds are going to stay the same, but it's going to start to rain a little bit, they might just put becoming light rain, for example, at a certain time. And sometimes they'll have a time range. So becoming between on the 10th at 5 o'clock and on the 10th at 7 o'clock, a bunch of stuff is going to happen. So for example, got another forecast here. So we're starting to add in more stuff, and it's going to get a little more complicated. So from the 10th at 4 o'clock, we see this block of stuff that we saw earlier. Becoming between 5 and 7, the winds are going to now become 180 at 15, 1 mile of visibility, light rain showers, overcast 2,000 feet. From this time, we're going to get all of this stuff. And then becoming between 2,300 hours, and then the next day at 2 in the morning, this stuff. And then from 260 at 1 o'clock, we'll see that stuff. So basically, we look for a from or becoming or a couple of other things, and then after that, we read all the weather description. And we can see already how the task starts to get a little bit more complicated than the metar to read, because there's just more stuff to read. Sometimes they'll put tempo for temporary. So if it's going to rain for an hour, they might just put a temp in the TAF, and they'll put the hours where they expect it to happen. So tempo on the 10th between 9 and 13 hours, some stuff's going to happen. So so here, for example, we have from this time this first block of stuff, and then temporary between 9 and 13 o'clock, we're going to get this instead. So temporarily, the visibility is going to go from 3 to 1. The rain is going to go from light rain to heavy rain, or to moderate rain, sorry. And the mist is going to stay the same. And then from this time, we get a whole new block of information that's off the screen. And then the last way they can describe things is they can give a probability. So if they say, it might rain, it might not, they can give a probability for stuff. So example here, we get a prob 30. So here they get a block at the start of a bunch of stuff that's going to happen, and then here they get a prob 30, which means 30% chance of something happening. So between 4 and 7, you get 2 miles of visibility and mist. So it might happen, it might not. All right, we're almost there, coming to the end. If they have extra things, if it's based on an automatic system, they will put forecasts in the remarks. They'll put forecasts based on auto observations. They'll usually also include next forecast by what time, so when we expect the next forecast to be. So there's that. So time for you to all try to decode the best of your ability is this. So I'll give you like 2 minutes, and then I'll go through it, and then we will wrap up. There's some more examples afterwards if you would like to practice more, but we don't really have time to get through those, so we'll let you take a look at this one. We'll give a quick, we'll go through it, and then if you have any questions, we will address those. So take 2 minutes, try to decipher this, and then I'll come back with the answer. All right, so let's go through it. So this is for CYOG. I don't know where that is, but that's the airport code. It was issued on the 1st at 1640 Zulu. It is valid. That's a weird block. That looks incorrect. It should say 0117/0217, so that it's valid from the 1st at 1700 hours to the 2nd at 1700. So that's just wrong. So the winds are from 280 at 15 knots. The visibility, or the winds will be, the visibility is expected to be more than 6 statute miles. Expecting light snow rain. It's a little bit of a weird way to do that. Clouds expected to be few at 1,500 feet. Overcast, there's an extra 0 there at 040 feet. So that's the weather we expect at the start of the period. Then temporarily between, there's some weird stuff in this copy pasting here. 17, whatever the time is, it's all messed up there. The visibility is expected to be 2 statute miles, light rain, mist, overcast 1,500 feet. Then from this time, we expect it to be 280 at 15, more than 6 miles of visibility, broken 3,000 feet, broken 25,000 feet, temporarily. We're giving these in weird formats, between 0 and 3, light rain showers. And then from 10 o'clock, the winds will be this, more than 6 miles, sky clear. So that's the way we read these. There are many more things to look through if you would like. If you would like to find more examples for whatever airport of your choice, you can just Google Nav Canada AWWS, or just go and actually I'll just put the link in there just for fun in the chat if you would really like to go and grab some real ones, have fun. Any questions? If not, we will wrap it up here. Last call. We have reached our... All right, if there's any quick questions, feel free to throw them up in the chat for the next couple of minutes. I'll get to them. If not, go through the form as usual. Submit your questions. Thanks for joining. Have a good night.